Hello and welcome back to our follow-up video on inverse kinematics, where we are concluding our little mini-series on forward and inverse kinematics. If you haven't seen the video on forward kinematics, you might want to take a look at that one first, if that's something you're not familiar with, because it's certainly the more straightforward of the two. Inverse kinematics are used when you have some position in space that you want to extend either a robot arm typically or a virtual arm towards, or you want to back calculate where a virtual arm would be given a hand position. So an example of that would be in VR, where you want to develop an amateur that's realistic to the user based on where their hand position is. You can back calculate where the forearm and upper arm would likely be. Or even in 2D animation, where you have reactive animation based on where a hand or foot position is, where would the arms and legs be. So that is the idea of inverse kinematics, and it's used quite extensively currently with different computer graphics and robotics. But you do need to, of course, know the endpoint that you want the arm or hand to be at, and the length of the links in the robot, or the length of the arm pieces. So let's take a quick look at what inverse kinematics looks like and what we're interested in. So similar to our forward kinematics, we'll do kind of a similar sort of angle here, or these links that we're interested in. So we have one length of length L1, a length of length L2. We do know that. And we know the position that we want the end of our robot to be at, our hand to be at in space, or our hand to be at to catch some object. What we don't know and are interested in is what is the rotation at the elbow, theta 2, and what is the rotation at, you could say, the base or shoulder, theta 1. So this is a little bit of a kind of multi-step process here. The first thing we want to do typically is find theta 2. Well, actually, part of finding theta 2 is going to be in finding what this length is here. So if we have a point xy, we have our links, right? We have L1, we have L2. That was terrible. L2. Part of what we want to know is what is this length between the origin and our final endpoint. And we can discover that pretty easily because we know what the x and y components are at the endpoint. We can create this right triangle. And so since we have a right triangle, we can, of course, use Pythagorean theorem, where we can solve P based on, we had this as opposite and adjacent, but you could also write it as px squared plus py squared, right? And that's going to give us our length on the long side of this triangle of our links that we're interested in. Once we know that, we are able to figure out what our gamma angle is. And let me explain what that means. So we know what P is at this point, and we know L1, and we know L2. So we know three parts of this kind of weird triangle that is not a right angle, obviously. But, oops. So we are able to figure out what this gamma angle is, and based on that, let me kind of fix some of this. Based on that, we are able to figure out what our theta 2 is. Because we know that theta 2, this is like not really working out well in terms of drawing this well, but we know that theta 2 is going to be equal to 180 minus gamma, right? Because this angle we know is 180 because it's a straight line that's being bisected between angles gamma and angle theta 2. So if we can solve gamma, we can solve theta 2. And we can solve gamma using the law of cosines. Now, the law of cosines is really useful when you don't have a right angle. And it's the right angle is a special case of law of cosines. If you were to look at, in this case, if we say A here, and we have a 90-degree angle, well, cosine of this 90-degree angle A is going to go to 0, and then we have the Pythagorean theorem, right? So we are going to use that to figure out what our gamma angle is. Okay, so in this case, we are going to have p squared equals, well, this will be L1 squared plus L2 squared, doesn't really matter which is which, minus 2L1 times L2 cosine of gamma. Okay, and we know all of these pieces at this point except for gamma. So we can solve our gamma, just doing the algebra and trig. So then we can solve our theta 2 as 180 minus alpha there, but really gamma is often what this is referred to as. So at this point, we now have theta 2. So we're halfway done, sort of. Already did that. So the trickier part is finding our theta 1. And it becomes even trickier because from our point here, all right, we've got theta 2, we've got theta 1, L1, L2. Now, we've started out with this sort of robot, but it's certainly important to understand that there's more than one solution in inverse kinematics, because you could have, something like this with a negative theta 2, right? So this is a positive rotation. This is a negative rotation. And when you rotate around this angle, or this side P that we constructed, you have basically infinite number of solutions, but within a plane you still have 2 for a positive and negative theta 2. So it is important to understand at least that there's multiple solutions and which solution you're looking for. And this may be the result of limitations of your robot, like you don't want your robot smacking its elbow into things, or you don't want your VR amateur's elbow bending backwards and freaking people out, right? So you need to kind of be aware that you can mathematically get 2 different solutions out of this. So, okay, so how do we solve theta 1? Well, what we can do, now remember, we have our x and y components of this point P. Sorry if you can hear my stomach growling. So this is going to be px, this is going to be py, and we've constructed what I call, and some people maybe call, a beta triangle. So we have a right triangle here that we're going to use to find this angle, beta angle. In addition to that, we need to know what this angle here, alpha angle, is. Because if we know these two, then we can find our theta angle. So we want this angle up to the elbow. And we can find our beta angle because this is a right triangle. We can also find our alpha angle because we know many other bits of information about this sort of weird shaped triangle, enough that we can again use law of cosines. And if we have those two, then in this case, theta 1 is going to be equal to beta triangle minus alpha triangle. However, again, remember that if we were using the negative theta in this case, and it changes in different quadrants, but this would be our alpha angle in this case. So, and we would be interested in this theta angle. So our theta angle for this sort of orientation would be theta 1 would be equal to beta plus alpha. Okay, so that's an important part to be aware of as well, that you can't always use the same equation to find theta. It depends on the orientation. Alright, so for this orientation, either way you got to find beta and alpha, right? So let's go ahead and solve for beta because that's fairly straightforward. Our beta angle is going to be, actually you can do this in different ways, but we already know the opposite and adjacent. We also know the hypotenuse, but we can use the py over px to solve for beta. Right, and this again is going to be different in different quadrants. So you're going to have, to think about which quadrant you're in and solve for it accordingly. But that's how you would do it in the quadrant 1, and it's really not that difficult to adjust for other quadrants. Okay, so and now we have our beta angle, but we need this alpha angle, right? So in this case, we can again use the law of cosines. So if we call this now side A, then a squared equals, well, actually, let's not do that because that's going to be confusing maybe. Sorry about that. Let's change this so that we have L1 and L2 in P. So our L2 squared is going to be equal to our L1 squared plus our P squared minus 2 L1 P cosine of alpha. Yeah, sorry. Okay, so from that we can solve what our alpha angle is because we know everything else, right? We started out knowing L1 and L2, we found P, so we're fine. So we now know, I hope I've been saying theta 1 and not theta 2. We know our beta angle, we know our alpha angle, we can solve for theta 1. And at that point, we know everything that we need to know, right? So just to kind of quickly summarize everything, we started out with a point of interest. We knew the length of this forearm, we knew the length of the upper arm or whatever, but we didn't know theta 1 and we didn't know theta 2. But by using the beta triangle and solving for our alpha angle and solving for our gamma angle, we were able to figure out what rotation is needed at the shoulder and what rotation is needed at the elbow in order to get our hand in position at point 1. Okay, well, I hope that was informative for anyone who was curious on how inverse kinematics works. If you have any questions, please leave them in the comments. I'll try to get to them within a day or two. But either way, thank you very much for watching, and we'll see you in the next video.